All right, the last thing from 4.4 is a special type of application of integration. And then we're also going to do 5.1, which is also another special application of integration, application of special type of area under the curve. All right. But right now, 4.4, we're looking at the average value of a continuum. And again, average is something we should understand. But it's actually a little tricky to find when it's a continuous function. But we still need it. There are a lot of applications that require us to find the average value of a function. All right. So remember what average is. This is, again, a concept you should be fairly familiar with. Again, your grades are based on averages. GPAs are based on averages. Most of the world runs on averages, all right? It's the average value of a function, average value of your grade on exam scores and homework. It's the mean. That mean is the same thing as average. It's you add up all of your scores and divide by your total. Same thing's going to be done here, except remember it's an infinite number that we add together, but that's what the integral symbol does. The integral symbol adds up all the function values. The hard part is, remember, we sum all the function values, which is that special limit, which we solve with the fundamental theorem of calculus. And how do we divide? All right, that's what we need to know, and how do we divide. So that's what this first one is going to be, kind of setting up where it comes from. All right, so we want to expand averages to infinite or uncountable sets, which would be a function, right? There's infinitely many values on a function, infinitely many values between any two moments. All right, and a couple of examples where this is used if we're finding the average temperature for a day. All right, technically, if we found the average temperature for a day, we'd have to find the temperature continuously, right? Because the temperature changes continuously. All right, there are an infinite number of times during a day where you could take the temperature. Right? All right, so if we wanted to find it, well, there's a few ways we could do it. Well, suppose we just kind of generalize it. And so I'm going to run through an example. All right, just kind of remind you what average is and based on this temperature. All right, suppose I want to know what the average temperature between midnight and noon was on a given day. All right, so again, the answer depends on how much data you collect. All right, how much we know about the temperatures yesterday. All right, suppose that we took two temperatures. At midnight, it was 65 degrees Fahrenheit, and at noon, it was 81 degrees Fahrenheit, and I use those to average out the temperatures, which means I take my 65 and my 81, add them up, and divide by 2, and so we'd say our average temperature for that time period was 73 degrees. All right, well, this is fine average, but it might not be super accurate, so suppose we decide to do another temperature in the middle of the day, halfway through. All right, so we take three temperatures. At midnight, at 6 a.m., and at noon. All right, so again, 6 a.m. would be halfway between noon and midnight, and we average those. So now I've got three values, and I'm going to find their average. All right, so I add up my three temperatures and divide by 3. I'm probably getting a little closer to what the actual average is. All right, well, suppose I tried to get a little better. I collected a little more data. I decide to take the temperature every hour. All right, and I didn't write them all down. All right, but suppose I had taken them every hour and wrote them all down. So again, they'd be slightly increasing every hour, and I'd add them up, and there'd be 13 temperatures because there'd be the start and the finish, right, and the hours in between. And so this is my new average, which I'm getting a little better at it, right? Getting a little more accurate. Well, what if I did it every minute? What if I did it every second? What if I did it every half a second, a nanosecond, and so on? Well, what we're doing is we're gathering more temperatures, right? Gathering more data. Every time we gather another piece of information, we get a little better. And every time we do have to divide by a slightly bigger number, right? Every time I gather more information, more temperatures. And so the temperatures span the time interval midnight to noon. Well, what if we decided to take infinitely many temperatures? There technically are infinitely many times I could take the temperature. Well, what if I decide to take them as they approach infinity? All right, and again, I go take a temperature every minute, every second, every half a second, every tenth of a second, every nanosecond, and so on. Well, that's what a limit is. All right, that's what we're looking at, a special type of limit when we do that, right? As limit as our temperatures go to infinity. All right, and so what we're going to do in general is we're going to generalize this. All right, so now looking at it in general. Excuse me. All right, we want to find the average value of a given function over an interval. Average value of the temperature over the time period noon to midnight. All right, well, first we divided into 2 temperatures, 2 times. All right, then we divided it into 3 times. Then we divided it into 13. And however many minutes there would be in between those times, we divided there and keep going. And so what we're doing is we're dividing it into even intervals, right? N subintervals, each with the same distance. Well, this should start to look familiar to what we talked about in the earlier sections. I can find the temperatures at the beginning of the time periods, at the end of the time periods, and I can add them up, right? So suppose I find the average value using the left endpoints, or the right endpoints, or the middle endpoints, and divide by however many we have, right? We'd have n subintervals, and that's what we'd divide by, right? When I had 2 temperatures, I divided by 2. I had 3 temperatures, I had divided by 3. When I had 13 temperatures, I divide by 3. All right, well, I divide by n, because I'm going to break it up into n temperatures. All right, and so what I'm going to do in the next step is, this is getting close to, I want to find basically a sum of my function, right? That's what we're looking for. I want to find the sum of my function values from point A to point B. Well, an integral does that, but I'm not quite to my integral yet. I don't have the delta x in there, right? The limit definition of the definite integral is delta x times my function added up together. Well, I don't have delta x, but I've got n. And so what we do is we manipulate it to get my delta x. And so what we do, again, so this is some algebra trickery, I want to get delta x. That's what I'm missing in this expression in order to use my limit of my Riemann sum, right, which I can solve with the definite integral. And so what we do is, well, I need the b minus a, right? The b minus a divided by n is my delta x. Well, I can't just randomly put b minus a in there. I put the multiplication of 1, right? B minus a divided by b minus a is the same as multiplying by 1. It's just a more complex one. All right, then we move stuff around, and all we did here is I moved around. Basically, what I did in this step is I moved this over, right? Move the sum of my function values over. I paired n with the numerator, right? That's what my delta x was, b minus a over n. And so that's where that delta x comes from. And then I still was left to, when I pair those together, there's still a 1 left over. And so that's where this 1 divided by b minus a is. All right, and so that's all that we did is, again, some algebra trickery to get there. And you don't have to know how to do this. It's just showing you where the average value function comes from. All right, so now I've got, again, it's still the average value. It's still this, but I've just manipulated it to get it to look like what I need. And what I need is f of x times delta x, right, every single time. And that's what this is. If I distributed it, it would be f of x 1 times delta x, and I'd have my Riemann sum. All right, now I do have an extra part to it. There's this 1 over b minus a, but remember, a and b are just numbers. So it'd be like 1 over 10 minus 4, right? And so remember, with the limit, I can pull that out, right? It's just a constant. I can pull it out front. And so I've got this constant out front, and then now it's the limit of my Riemann sum, which I can solve this. Now this is the limit that I know how to solve using the definite integral and the fundamental theorem of calculus. Right? That's what that limit is. This is the limit of the Riemann sum, which we know equals the integral, and it can be found using the, that 2 should be there, fundamental theorem of calculus, FTC, fundamental theorem of calculus. So I know how to solve it. And so what we do is, well, that's this integration. So the average value of my function equals some function value at c. All right, so this is the average value. So again, somehow mine got shifted. So that's the average value of my function. All right, which again is 1 over that b minus a times the definite integral. Remember, this is the sum of my function values. That's this limit, the sum of my function values. And in the average value, we have to divide usually. Well, what it turns out is we divide by the distance we traveled, right? I'm finding the accumulated sum of my function from a to b, right? And so average value is I add up all the values I want to take the average of, and then I divide by the total. Well, there's infinitely many, so we can't divide by infinite. But what we do is we divide by how far we traveled. So if I'm finding my average value from 2 to 10, we traveled 8 units, all right? And so we divide by 8 units, all right? We traveled 8 units, all right? That's the distance at which we traveled. All right, and this is just an alternative way to write it, all right? F average times so basically we just move the b minus a to the other side, right? I multiplied by b minus a, and so that's just an alternative way to write it. All right, so those are the two forms of the average value. All right, so my average value equals 1 over b minus a, integrating from a to b of my function with respect to x. All right, which is the same as taking b minus a times my average value equals that integral. All right, that's just the two ways that I've written it. Since mine were kind of weird when I cut and pasted it into this program, I'm just rewriting. All right, so what's going on graphically? It's always important to understand what's going on graphically. All right, so suppose I have a function. All right, so here's my function f of x. All right, and I want to find the average value between a and b. All right, so there's my a and b, and so this would be the distance we traveled. That would be b minus a. So if a was 2 and b was 10, we traveled 8 units. All right, and that's the number out front. And so when we find the average value, right, the average value would be my function value's average, right? It would be taking the sum of all of these function values and adding them up. Well, that's what the integral does. It finds the sum of all. That's what this is doing. Finding the sum of all those function values, add them up. And then we divide by the distance traveled. All right, my average, my function's average, is my 1 over b minus a, integration from a to b, f of x dx. All right, this is sum of all my values, and this is what we divide by. And as it turns out, what's happening there, so this dotted line is going to represent my average value. This would be the, again, whatever the function value's average is, right? And it is a function value. And so what we get is we get this rectangular shape, right? Which is where that second formula comes from, right? This distance here would be my average right up to this point, right? That's my average. And then this distance here would be b minus a. And as it turns out, the area under my function, so if I highlight the area under the function, right, this would be the area under my function, which is my accumulated sum. Which is this integral part. Right, that's what that area represents. This is my average value. All right, and this rectangle area is actually the same as the area under the curve. All right, and so that's what that, again, what happens is the area of that rectangle is equal to the average value times b minus a, right? That's that rectangular area, and I'm going to switch back to my pen. And that's what that second formula is, right? That's the rectangular area, my average value, times b minus a equals the integration, the area under the curve. All right? And that's something that unique happens with our average value find. That's sort of what's going on with the average value find. Now we're just going to be finding it. We're not going to really do a whole lot with areas. But it is important to understand that's what's going on. That's the behavior of it when we find it. Again, we're going to just be finding the average value, so we're just going to be solving this. All right, but this is what's going on graphically. All right, so now we're just going to practice it. Find the average value of my function over the given interval 0 to 4. So I want to know what is the function's average from 4 to 0. All right, on average, what's my function value? And so the average value, the function's average value, is 1 over b minus a, integrating from a to b of my function f of x dx. And so for this particular function, there's my A and my B. So I'm going to write it out, although you could just divide by 4. But I'm going to write it out so you know that I am subtracting A. A just happens to be 0. And then going from A to B of my function 4x minus x squared dx. And then we solve that. All right, so I have the 1/4 out front, and it's important, don't lose the 1/4. And then we solve it again. You can solve that on the calculator. All right, so you'd graph out the function and solve it on the calculator. So again, I'm going to go to the calculator, type in my function 4x minus x squared. I'm going to do a standard window, so I'm going to go to Zoom Standard. All right, so there's my function. I'm integrating it from 0 to 4, so it's going to find that whole area. So 0, second trace, 7, integrate 0 to 4. All right, so 10 2/3. Or 1/4 times 10.67. Again, I'd be okay with fractions. And so don't forget the 1/4. It's really easy to forget the 1/4. All right, so it comes out 2 6/6 repeating, or 8/3. All right, so that's the average value. So my average value of my function between 0 and 4 is 8/3, or 2.66 repeating. All right, second example. Find the average value of my function 2e to the x from negative, oops, that one needed to be changed, from negative 3 to 2. All right, negative 3 to 2. I meant to change it and I forgot. All right, so my a would be negative 3, my b is 2, and so my average value of this function, again, first thing we do is we take b minus a, integrating a to b of my function. And so for this function, my b was 2, my a was negative 3, times negative 3 to 2 of my 2 u dx. Alright, so up front I have 1/5, right, because it's 2 minus a negative 3 means I add the 3. Integrate from negative 3 to 2 e to the x dx. And so I get 1/5 times whatever the 2e to the x dx is. Alright, so again, clear this out. 2 e to the x. And then second trace, 7, negative 3, positive 2. And I'm going to give myself plenty of decimal places, so 14.6785. So 14.6785, and then don't forget, that's just the sum of the function values. It's adding up, like when we find our averages, we'll be adding up the sum of all your exam scores. That's what this is doing. This part's adding up all the function values. That's what the sum of the function values are, and then we divide by 5, because that's the distance we traveled. We traveled 5 units on our function. Alright, and so then that average value comes out to be 2.936. So our function value has an average value of 2.4. So again, if this were talking about money, alright, the sum of the money between 2 to negative 3 to 2 would be $14, but it would be averaged out over 5 intervals, and so it'd come out to $2.93. Alright, that's the average. Alright, so we're going to look at some applications. Alright, applications of average values. Alright, so to put it in a little bit of context, alright, so we've got a concentration of a blood. So a patient's given a drug, right, given an IV, pill, something. Alright, the body breaks it down, and so, when they're first given the drug, there's a high concentration, and then after a few hours, it's been broken down, and there should be low or no concentration. Alright, so it decays exponentially. So this is an example, again, the body breaks it down exponentially, and so this represents the amount of concentration of the drug in the bloodstream measured in milligrams of drug per liter of blood, right? That's milligrams per liter. Alright, find the average concentration in the bloodstream, and again, I changed yours and I forgot to change mine, from 5 minutes to 10 minutes, alright, after you've been administered the drug. Alright, so what was the concentration of the drug in the blood 5 minutes to 10 minutes after you've taken it. And it'd be in milligrams per liter. All right, so the concentration, the average concentration, average amount of drug in your bloodstream between 5 to 10 minutes after you were given the IV or whatever, is found by taking, again, B minus A, integrating from A to B of our f of t function. All right, so average, well, it's 5 to 10, so 10 minus 5, integrating from 5 to 10 of that 8e to the negative 0.05t. All right, so I'm just going to find it. I'm just going to plug it in the calculator, and I'm going to get it. So this is 1/5. Don't forget the 1/5. You find this on the calculator, so you graph that, shade the area between 5 to 10, and then make sure you give yourself a few decimal places so you're not rounding too much. And so when I plug this into the calculator, it comes out 13.296, which again, that would be the sum of the concentration. That would be it for every moment between 5 and 10. If I added up the concentration level for every moment between 5 and 10, it would add up to 13.29. I'd divide by the time period because it's per minute. And so 5 minutes had gone by, so the average is based over the 5 minutes from 5 to 10. And so the average concentration of the blood in the bloodstream would be 2.6585, or around it to 2.7 milligrams per liter. All right, so from 5 minutes to 10 minutes after you were given the drug, the concentration level on average was about 2.7 milligrams of the drug per liter of blood. Right, that's what the milligrams in the liter is. It's milligrams of the drug per liter of your blood. All right, so on average, you're a little less than 3 milligrams per liter of blood in your bloodstream. All right, the last example. Manufacturer determines that T months after introducing a new product, the company's sales can be estimated by this function. What are the average monthly sales over the first 6 months? So we want to find the average sales over the first 6 months. The first 6 months would be from time 0 to time 6, right? It's in months, so it would be those first 6 months. And so we'd find the average. Again, we'd take B minus A, integrating from A to B of our, oops, not M, N of T. All right, so our B would be 6, our A would be 0. So 6 minus 0 is just 6. I'm leaving off the minus 0. All right, 0 to 6, that's 750t, divided by the square root of 2t squared plus 25. And again, this one you actually have to solve with the calculator. You actually can't solve this by hand. So this is one of those examples where you have to use the calculator. You cannot find this integral by hand. All right, don't forget the 1/6, because that's what we divide by, right? It's over 6 months. We're averaging it over every month for 6 months. So there's 6 months we're averaging it over. The sum of the sales from 0 to 6 would be this integral, right? That's adding up all of the sales over that first 6 months. And then we're dividing it by 6 in order to average it out. Just like if we had 5 exams, you'd add up all your exam scores and divide by 5. Same idea. It's just an accumulation function instead of numbers you can actually add together. All right, you plug that into the calculator. Make sure, again, you're careful when you do that. Shade the area from 0 to 6, and it comes out 18.1832. Which again, that's just the accumulated sales. That would be the net gain in sales from 0 to 6, and we want to average it out over the 6 months. And so you can't forget to divide by 6. And so the average sales figure per month is 303. So again, on average, over the first 6 months, they averaged about 303 Didn't give me units, but I'm assuming it's in dollars. In sales per month. All right, that would be on average. Now, some months they might have gotten more than that, some months they might have got less than that, but when it averaged out, there was about $303 in sales per month, all right, for the first 6 months. All right, so that finishes up the average rate of change. That actually finishes up chapter 4. All right, so we're done with chapter 4. The last section we're going to do is a special application. That's one of those applications we're required to do, which is the consumer surplus and producer surplus. All right, and that'll be that, and then we're done. All right, we have one more application type, and then we are through for the semester. All right, so again, we will stop this video there.